Okay, yeah, thank you so much for having me and for everyone for coming today. And yeah, like Abby said, I'll be talking about how water ice evolves on Mars and yeah, what implications there are for liquid water today, which has always been of interest. Quick sort of informal introduction of myself. Um, I do a bunch of things. My favorite thing I'd say is snow and ice and trying to figure out what's happening to it using radiative transfer, what's happening in the atmosphere near the surface, how the climate evolves, and then using data from satellites through remote sensing and analyzing what the features uh, are on the planet, and as well as if there are connections with life. I've also do a bunch of other things from football or soccer to photography, and I just moved to Seattle and started this job a few months ago. And like Debbie mentioned, I'm hoping to do more work on ice on Earth as well as other places. So if you have ideas, uh, yeah, let me know. But okay, a brief respite from maybe what's happening on the Earth. We can go to Mars, which is similar but also dissimilar to the Earth. The atmosphere is pretty different. It's mainly CO2 with much less atmospheric pressure near the surface. It's also very dry. The amount of water in the atmosphere is about 0.1% of the Earth's. The gravity is much less, and yeah, currently there are two robots functioning. On the right, uh, this is an image from the Viking lander, where there's actually frost, so it's formed on the surface, deposited on the surface, near the Viking lander on a bunch of rocks. And this is before we've had better technology to figure out what's an ideal place to land, which is why this place is strewn with rocks. And yeah, we were really fortunate that we landed safely in this sort of. You compare this to where we land these days, and it's always flat because we can now check to see where the rocks are and avoid them. But Mars has a lot of ice, and hopefully that's what all of you enjoy. So these are some false color images in a different variety of settings. But it turns out a third of Mars has shallow buried water ice under the surface. And so the image on the left, I'm going to turn on my laser pointer. And oh, wait, to right click, pointer options. Yeah, so the image on the left, the bluish material is water ice. It's exposed on these steep cliffs. You may have seen something similar on the Earth in these permafrost sort of cliffs, but I want to emphasize this is uh, we think ice that formed from snow. It's not a lens of ice. It's about 100 meters in thickness, and we'll go into kind of how it formed later. But all the yellowish material is non-ice material. Then on the right, in the center rather, there's turns out because the atmosphere is so thin, there are things crashing into the surface constantly on Mars, and because a third of the surface has shallow ice underneath, it gets excavated if there's ice there by these craters or these yeah. And so here you have ice exposed at the surface by an impact. And then in one place on Mars, at sort of Canadian latitude, 68 degrees north, we landed the Phoenix mission 10, 15 years ago, and it dug 5 centimeters down below the surface and exposed water ice at the surface. So in one place on Mars, we actually have in situ measurements. Why is ice important? Just like on Earth, we think it shaped the landscape. For future missions to Mars, it could be a resource for fuel and water. If it's melting, it might host life. And just like on Earth, here's a core taken from Antarctica, and another one of those scarps or cliffs where the bluish material is water ice. And then you might be able to discern these layers of ice and dust that you see exposed. And so the idea is if you can obtain or drill into this ice and get a core, just like on Earth, you could then understand the gases and by analyzing the gases and the sediments trapped in the ice, you can figure out what happened when the ice was actually in place to figure out the climate and its history. So, okay, well, how does the ice even get there? So it's basically a form of an ice age where um, on the left, we're just saying if Mars is a planet and it has a tilt, which we're calling the obliquity. If the sun is shining from one direction and the planet is tilted at high angle, high obliquity, then if there's any water ice at the poles, it's going to get heated up. And there it generally turns into gas, it sublimates, and then it precipitates then, we think, at the colder now equator or mid-latitude sort of regions, because the sun is focused on the poles. And at low obliquity, it's the opposite, where if you have water ice at the mid-latitudes, the sun is now focused on those regions, and then it migrates to the polar regions. And on the right, this is a calculation of how this angle or this tilt has changed over the last 10 million years. And currently, it's close to Earth's value of 23 degrees, approximately. Mars is about 25. But you can see it's actually oscillated a lot from 15 to all the way up to 45 over the last 10 million years. And so on Earth, we have ice ages that come from relatively small oscillations, a few degrees. On Mars, it's very extreme. And the reason for this is on Earth, we're being pulled by the sun, which is massive, and Jupiter, but then we also have the moon to sort of stabilize us. But Mars has these two feeble, smallish moons that aren't gravitationally big enough to stabilize Mars, which is why it goes through these crazy oscillations through time. And so first, I'll sort of expose this what we observed a bunch of years ago in these gullies on Mars, and I'll explain what those are. So on the left, we have an image of a channel formed from snow melting in Canada. And so here's the snow, and here's the channel cut into this rock. And then on the right, we have an image from Mars that looks remarkably similar, where you have rock, wall rock, and then you have these channels. But the question is, where's the snow on Mars to actually form these channels? And so over the last, let's say, few decades, people have been looking at images from Mars. And we're actually lucky because they flew a military camera to Mars and it can see things the size of the table you're probably sitting at, about 25 centimeters per pixel. So here's an image from Mars at the sort of red wavelengths, about 700 nanometers. And it's a wall of a valley where you have wall rock and then these lobe-like features that people call the mantle. And when they were first sort of discovered, what people noticed was they were found on these pole-facing slopes only, polewards of 30 degrees latitude. And people thought they had ice inside of them and it would be stable. Another thing they noticed was often these gullies or channels were eroded into the mantle. And they were also noticed that they were on top of the rock. So Phil Christensen, my PhD advisor, was calling them pasted on terrain because they look like they've been stuck onto the wall. But before 2021, no one had actually seen the ice inside of these mantle materials. So they were just called the mid-latitude mantle. And so today we're going to expose the secret of the mid-latitude mantles. So here's that same valley wall. It's actually a zoomed out image. You may be able to discern faintly these flow lines that seem to be emanating from the slope, which we think is either a Martian ski slope or maybe it's something else. So let's take a closer look with the high-res camera. And this is at 33 degrees south, I should point out. So here's a high-resolution image from that same area. So on the left, we see these channels cut into the rock in this sort of hollow. And then on the right, there's another sort of hollow, except it's filled in or covered by this thing called the mantle. And we see a channel cut into it. And right inside the channel, nowhere else do we see exposed dusty ice inside the mantle. And so we began noticing this at a bunch of places. So here's another sort of interesting place. So it's a triple crater. So three things sort of impacted the surface almost simultaneously. And here's the mantle again, all the pole-facing wall stuck on top of the wall rock. And here at the bottom, you may see what maybe could be a moraine. Anyway, let's take a closer look. So here's a zoomed in view. here's the mantle again. You may be able to start to discern these light tone patches where the ice is exposed in the mantle by these gullies. If we could take a closer look, maybe more clearly, you can see ice being exposed. And so we think these things are basically buried debris-covered glaciers that on steep slopes, slumping exposes the ice. So if we zoom in here, here's the rock underneath that's sort of modeled. We think as the ice is sort of moving and sliding down, it's weathering the rock underneath. And then only within this thing called the mantle, we see ice exposed at the surface on these very steep slopes. On the left, you may be able to discern these polygonal fractures that we see on Earth as well. And they're thought to form as the sun passes overhead, it's heating and cooling the surface. And ice, if it's below the surface, will expand and contract, which would then cause these fractures. So we've seen them in Antarctica and the polar regions of the Earth. And they're again an indicator that there's ice below the surface, which on the right we're seeing exposed at the surface. And so these are some false color examples of different places where we found these ice exposures. We don't know if they're the exact radius of the grains, which is one indicator of whether it's snow or glacier ice. So we're just calling them ice. And we did analyze their brightness or the albedo, which we'll discuss shortly, to find that they have less than 1% dust. And normally they're covered by this desiccated dry material. And sometimes this dusty ice gets exposed on these steep slopes, like I mentioned, by slumping. And what's particularly significant about what we found was one of the places we found this ice. It represents the most equatorward detection of ice on Mars to date, about 33 degrees south. And that's significant because if we're trying to send missions to Mars, we're trying to get as close to the equator as possible because it's warmer, there's more sunlight. And also if we're trying to assess if the ice is melting, it's more likely to melt closer to the equator because again, there's more energy for it to melt. It's warmer. So luckily, this orbiter, the Mars Reconnaissance Orbiter, is actually still orbiting Mars and you can request images. And 11 years later, we got a new image. So we're showing 2009 versus 2020 back and forth. And I'll zoom in a second. So note the scale again. There's 100 meters. Here's in America, they love football fields. So here's a football field for scale. And if we zoom in, these arrows are essentially pointing to here there's a new sort of 50-meter channel that wasn't there before. The lighting conditions between the two images are very similar. So we don't think it's shadows. We also assessed if it was shadows. And then it looks like the ice has disappeared. And it's not clear if it melted, if it sublimated, if it just got covered, if it formed a lag of dusty material, because turns out greater than 1% dust within ice can appear like dust alone at these wavelengths. And we'll go through why. But the question is, what's happening to the ice? Are we seeing evidence of present day melting? And oh yeah, here's a football field again for scale. So can ice on Mars melt? So everyone probably hates this diagram. It's a very simplified view of the different phases under equilibrium of water. And note the axes are the temperature of H2O and how much H2O there is, as in the vapor pressure of H2O. And so this example is from my PhD defense of a bunch of years ago, where in Arizona that day, it was 58 Fahrenheit, about 40-something% humidity, which we can convert to Kelvin, 287 Kelvin, about something 40% relative humidity. And so for ice to be stable at the surface, we can use one of those curves. And so at 287 Kelvin, you need about 16 millibars, which would be 100% humidity for ice to be stable. The same number of molecules of the surface leaving would be replaced, and you would have stable ice. But the actual humidity was about 43%. So if we plot that sort of on the phase diagram, you take an ice cube out of the freezer and you put it on the table. As it heats up with 43% humidity, relative humidity in the near surface, it'll turn into liquid, and then you keep heating it up, and it'll turn into gas, so it'll evaporate. And that's consistent with what we see. But remember on Mars, the amount of water is 0.1%, so it's way less, very dry. And so there, if you take out ice from a stable location and you put it at the surface, the stable phase is gas. It'll sublimate, it'll turn into vapor just because it's very dry. And so because of this, there was this famous paper in the journal Science by Andy Ingersoll at Caltech in 1970. And the key conclusion was ice cannot melt on Mars because the evaporation rate is so high that there's just not enough energy to melt the ice. Because when we evaporate, it requires energy to change phase. So that was the conclusion. So can ice on Mars melt? Guess not, right? But what if it's melting below the surface? So within the ice, air is actually saturated, which means there's 100% humidity, which if we go back to our phase diagram, and if we have melting below the surface, then you would have stable liquid water. Because if we go back to our phase diagram, at the melting temperature, and you have 100% relative humidity, if you heat up ice to the melting point below the surface, that liquid could be stable. So now let's see if that's even possible. Is there enough energy to melt ice below the surface? So to do that, we have to consider the energy balance. So there's deep from inside the planet, there's some amount of heat. Then there's conduction, like when you touch a hot object. Then there's solar radiation, which actually goes through the ice because ice is translucent. And then there's energy to and from the atmosphere through these turbulent fluxes. And then we all are at our temperatures radiating in the thermal infrared. And so turns out on Mars, the two biggest contributors are solar radiation and turbulence. And of course, people have done this sort of modeling before, but there's some limitations, particularly for these two key factors. So for solar radiation, there's some important factors to consider with ice, and which are dust and how big the snow grains are. And I'll show you that when you include those factors in the calculations, you can have 10 times more heating. The problem is all current Martian ice models ignore the amounts of dust in ice and find that no melting occurs, except for two models by Gary Clow and Guy Williams. And they both actually find the dusty snow on Mars can melt today. But there's still some simplifications in their models, especially with the turbulence. So the turbulence depends on how the wind changes with height, as well as the humidity and temperature. And this can lead to more or less cooling, depending on the local environmental conditions. And there were some indications a while ago saying that maybe the current Martian ice models were not calculating these terms properly. Anyway, so we'll go into these two key terms in more detail, maybe simplistically for some of you. So solar radiation. So here we're just sort of accounting and seeing what happens to light when it encounters a single ice grain, keeping track of incoming light versus outgoing light. So here's an ice grain. Let's say 10 watts per meter square is coming in. Actually, 80%, 8 watts per meter square gets reflected. Some of it actually goes through, it's transmitted because ice is translucent. And then a little portion gets absorbed, let's say 0.1 watts per meter square. So yeah, there's our animation. And all of this happens as a function of wavelength. So on the x-axis, we have wavelength. Here's kind of what our eyes see from red, green, and blue. And on the y-axis, we have this thing called the imaginary index of refraction. All that is saying is how much light is absorbed. And notice it's on a log scale. So we have more absorption and less absorption. So now if we plot the spectrum of water ice, and we bring back blue, green, red, we can see that ice absorbs the least in the blue and the most in the red. And also the absorption is pretty low. I know we haven't explained these relative units, but it's pretty low, 10 to the minus 10. And by looking at this, we can see why ice is blue when it's pure, when there's no air or anything else inside. And when you have enough of it, because it basically absorbs more of the red and the green, leaving behind only the blue. And so pure ice is blue. But Mars is a dusty place. So this is the InSight lander I think about a year afterward, and you see everything caked with dust. And they never use like wipers or anything. I don't know why. So the mission just ends once everything gets dusty. Um, but we have to account for this dust when we're doing our calculations. So here is the Mars dust spectrum. Remember, water ice was somewhere here. Mars dust is 10 to the minus 2, and it's the opposite. So it's absorbing the most in the blue and the least in the red. And that's why Mars dust is sort of reddish brown, as you can see on this image from the rover. And comparing the two, turns out they're about 8 to 9 orders of magnitude difference. So dust is 9 orders of magnitude more absorbing, especially at visible wavelengths. And what does this do? It makes it so that tiny amounts of dust can make a big difference and darken the ice disproportionately. And that's also why ice is fairly transparent, but dust is opaque. And this all goes into this thing called albedo. And low albedo is just something dark, where you're absorbing most of the sunlight. You wear a dark t-shirt in the sun, and it'll be warmer compared to a light t-shirt, which is of high albedo. And again, which is sort of the difference between snow and dust. And in equation form, all that's saying it's albedo is the reflected light divided by the incoming light. In our example, that's 8/10 or 0.8. So we can simulate this, and we calculated this working with an expert called Steve Warren at the University of Washington, who's been predicting the albedo, spectral albedo of snow and ice for the last 45 years. And so here's a simulation for pure snow, and here's albedo now on this axis, where there's more reflection at 1, less reflection 0. And pure snow, here's blue, green, red, would essentially look like that to our eyes. And here's pure dust. It would look sort of reddish brown, like we said, as we saw on the rover. Now, what happens if you mix them? So if you add a tiny amount of dust, 10 to the minus 4%, the albedo mainly reduces in the visible wavelengths, where ice is very weakly absorbing. So small amounts of dust can make a difference. It would look like that color. And you keep going, keep going, keep going. You get to 0.1% dust. 0.1% dust. And the albedo is now this purple line. It's dropped from 1 to about 0.2, dramatically lowered the albedo. And if you were walking by, you would see something of this color and think, oh, it's just dirt, but it's actually pure snow with just 0.1% dust. Again, because tiny amounts of dust make a big difference. It can darken the dusty ice mixture disproportionately. And so I'm sure you've seen this as well, when you see it snow and the snow has been there for a few days, it looks really dark and dirty. But I bet if you took it home and melted it, the amount of dirt would be very little, less than 1%. And so that's important, accounting for this dust, because it's making it darker, which would be warmer. The other thing that's important is how big the grains are. And over time, snow grains get larger. And so what's happening is, as the grains get larger, the chance of light being absorbed increases. So the probability increases of absorption as the grain size increases. And so snow basically transforms eventually into glacier ice, through this thing called firn. And so snow, it turns out, is mostly air. As you reduce the air with time and compression, it turns into firn, which is less air. And then gradually, when the density is about 830 kg per meter cube, the pores sort of close off and all the air is only trapped in the form of bubbles. And then you have glacier ice. And what's happening is, again, the grains are essentially getting larger and the chance of being absorbed increases. So you're getting darker. So you can see this in albedo form, where you have snow, which is one of the brightest subject things on Earth. And as you increase the radii or the grain size, it increases and the albedo reduces. So we're going from snow to glacier ice, and essentially the albedo is dropping up to a factor of 7 overall when you compare snow and glacier ice. And again, it's because the grains are getting larger. And a model is untrustworthy until you test it with actual data. And luckily on Mars, we have one place where we measured the light coming back from the ice as well as the nearby material. So here's the ice, here's the soil. And so the measurements are in the solid lines, blue and red. So here's the ice spectrum measured, and here's the soil. And we were able to match the nearby soil with just dust alone. For the ice, we noticed that if you just try different combinations of grain size or grain radius, we were never able to match the albedo, especially at visible wavelengths, until we added a small amount of dust. That's the black dashed line. So we found that you could match the albedo with 350 micron radius snow with a small amount of dust, about 0.01%. And then we also, there are these interesting measurements made by Matt Cooper in Greenland, where they actually measured how much light was coming at the irradiance, how much light was coming at different depths inside the ice as well as at the surface. And so here's the ice in question. It's glacier ice, so pretty dense. At the top, it was sort of granular. And here's what they measured. So the measured data is in the solid lines at the surface. So here is blue, green, red again. And this is the amount of light. And then at 12 centimeter depth, there's still a bunch of energy, which we were able to match with our model. That's the dashed line. And you keep going, keep going, keep going. At almost a meter depth, 77 centimeters, there's still a significant amount of energy that does vary with wavelength. And our model matches I would say, the measurements pretty well. Often, though, people will use one value to characterize the full spectrum. So they'll use a broadband flux value. So if you did that for 12 centimeters, you can compare this horizontal black line with the blue measurements or the model. And you can see you're basically underestimating the amount of energy at these wavelengths, but then overestimating the energy at other wavelengths. And so it's very important to account for the spectral variation of subsurface light, because this can lead to subsurface warming by up to 10 Kelvin. And we're trying to see if the ice can melt below the surface. So accounting for the energy below the surface is crucial. And to sort of summarize, these are the two results from before. What most Mars ice models do right now, what is the albedo of ice? It's 0.4. Again, they won't account for the spectral variation, which can again lead to 10 times more heating when you account for dust as well as how big the grains are. So these factors are very important. I had put this question in the middle of my presentation to check if you're awake. You don't have to answer it if you don't want to, but given what we've just sort of discussed, I just thought it'd be fun to then ask, okay, we just mentioned ice is blue, ice is made of water. So why is water in a glass transparent? And a hint maybe is that water in a glass looks transparent, but then in the Bahamas, it's blue when it's over white sand. And it's also blue on these melt ponds. So this is a picture that Steve took in the Arctic, Greenland, maybe. Yeah, so if you want, you can answer it. I'll give you whoever, I don't know, 15, 20 seconds. And if not, if there's silence, we can keep going. And I'll tell you the answer. So the question is, why is it transparent in a glass, but blue here? Okay, so the reason is it's just the amount of water. Turns out because water is not absorbing much at visible wavelengths, it is absorbing, but you need enough of it to actually see the effect. So I found this fun image on the right where you can see it's where there's less water, so the step is closest to the surface. It looks white because the light's gone in, which is white light. It's gone through some amount of water, but barely been absorbed, and then hit the white surface at the bottom, and then gone through water again and back out, but it hasn't gone through enough water for any effect to have happened. But as you get deeper and deeper, the last step, the light's gone in, the water, some of the red and green has been absorbed. It's hit the white surface, which reflects whatever came at it, and then it's gone through the water again, absorbing some more red and green, leaving behind the blue. So that's what blue light's left behind. And what you get at the surface is white for a shallow water. And if you have enough water, then you'll actually make it look blue. So it turns out it's about, 200 centimeters, or 2 meters. And here's the sort of text explanation. If you have enough water, it'll absorb the red and green, leaving the blue to reflect off the white surface, return to our eyes. Okay, so from that brief interlude, we can return to that diagram where we looked at the different components of what's happening to the light and just look at absorption. So when the light gets absorbed, it gets re-emitted in thermal radiation at these temperatures. And so here's that imaginary index of refraction again, which is the absorption, now as a function of thermal wavelengths. So this is kind of what snake eyes see. So if a snake was here in the room with you right now, I'd be happy to see you because you're all radiating in the thermal infrared. And there, ice and dust are different. They're actually strongly absorbing thermal radiation, unlike in the visible, where ice was very weakly absorbing, dust was kind of still strongly absorbing. And what this can lead to is this solid-state greenhouse effect, where you have sunlight going in to the ice, because ice is sort of translucent. It can go up to a few meters, heating below the surface. And so if you imagine a bunch of ice grains, hypothetically, and we zoom in at the top three, you have light going in, heating below the surface because it's translucent. Then if you imagine one grain radiating in the thermal after absorbing some of the energy, then the next grain is actually going to absorb most of that energy because we just said ice is strongly absorbing in the thermal infrared, and so on and so forth. And so until a tiny amount escapes then at the surface. And so inside the ice, what's happening is the neighboring ice grains are absorbing thermal emission from each other. So you're essentially trapping heat from sunlight below the surface, just like in a greenhouse, where the gas in the atmosphere, like CO2, it doesn't stop visible light. It's not, you can't see it right now, but in the thermal, it's actually absorbing energy, again, forming sort of a greenhouse. And this isn't fictional. We've seen this on the Earth. So this is from Antarctica in the Drowning-Maud region, where they were walking along the surface and they noticed, wait, there's no liquid at the surface. It's actually melting below the surface. And so they used a chainsaw to actually look at the water that was underneath the surface, and they measured the temperatures. And so at the surface, they found it was below freezing, -3 centigrade. Here's the melting temperature. But then about 25 centimeters down, where there's still enough sunlight, it was melting below the surface for up to 1.5 meters down to the surface. And then it was getting cold again. And so it's that scenario we envisioned where you have ice at the surface, liquid water, and then ice below. And so the question is now, what can this do? And so we had this idea that if these are those mantles again from a while ago, where we're seeing exposed ice, normally they're buried, but if you imagine part of it gets slumps down, you have ice exposed to the surface that has some amount of dust. And what might happen is if it's melting below the surface, and if there's enough ideal radiation conditions, if there's water inside the ice, maybe if there's life as well, lots of ifs, this would be a good place for life sort of to thrive. And we've seen this on the Earth. Things like cyanobacteria enjoy these sorts of conditions in polar. I don't know if they enjoy them, but they do live in the summer. And then in the winter, everything freezes up and they actually go dormant until the next summer or whenever they start melting again. And there's a video here of someone sticking a camera into one of these photosynthetic zones on the Earth where there's these dark sediments that, because they're dark, heat up and then actually melt through the ice. And then there's some liquid inside of them in these holes that form as a result, which then freezes. So at the top, you might be able to discern there's a lid of frozen ice, and below which there's some liquid. And then at the bottom, there's some sediment. And so they're called cryoconite holes. And we think we might be seeing maybe something analogous on Mars. But okay, so that was a brief, that's the guy. Yeah. So the question is, okay, is the ice on Mars also melting in the subsurface, which is what we're trying to figure out. So to do that, we have to look at turbulence. And so that's the other side of this diagram, another key factor. And a quick sort of basic overview. There are two types of airflow. You can have air flowing smoothly until it encounters these roughness elements or objects in the way. And then you get chaotic or turbulent due to friction or shear. And this is sort of dictated by the roughness of the surface. Or you could have airflow transition from smooth to chaotic or turbulent due to buoyancy. So here's some cigarette smoke. After a while, it can no longer sustain being a laminar smooth flow and gets turbulent. And on Mars, this is particularly important because water, the molecular weight is 18 compared to the atmosphere, which is CO2, and that molecular weight is 44. So it's much, water molecules are lighter than the atmospheric CO2 molecules. So more buoyancy occurs. So it's important to account for that. And all of this is happening in the atmospheric surface layer, which is sort of the lowest 10% of the full boundary layer, which can range from 0.1 to 11 kilometers on Mars, big range. That's also where the helicopter used to be. And yeah, kind of what's happening, some of it is determined by how rough the surface is. And what we did was we developed a one-dimensional model based on Earth. So there's a lot we're learning from people like you who study the Earth as well as other planets. And I won't go into these equations, but they're just saying the gradient, or how does the wind vary with height? It depends on the stress, shear stress, the density, and kind of where the magic happens in this diffusivity, how that gets transported. And we're using a modified version of this Manin-Nabokov similarity theory that's been used on terrestrial planets for the last 50 years, with modifications to account for what's happening right near the surface, as well as large-scale convection that's not included in Manin-Nabokov theory. And the nice thing is it can be used for any gas mixture. So you can use it for any rocky body with an atmosphere. So we tested it using data from the Earth, Mars, and Titan. But you could use it on exoplanets or, past Earth, Archean Earth, all kinds of things. And there are analogous equations for temperature and humidity, which I won't go into. And again, we wanted to check our model. So here's an interesting place. This is Lake Hoare in Antarctica. And it's actually an ice-covered lake. And so Gary, my co-author in the 80s, they were actually measuring how much ice sublimated, turned into gas over time. And so we wanted to compare the model that people use mostly today for Mars, which is by Dundas and Byrne, and compare that to our model. And so we're showing measured sublimation rate on the x-axis versus modeled. So if they were in perfect agreement, all the points would fall along this line. And we basically found that the Dundas and Byrne model was overestimating by a lot compared to ours, which did much better. And then one key factor, we thought, why is this happening? Is this large-scale convection? And so this is sort of a large sort of chamber where they put metal grains, and they're heating up with this heating rod, the whole chamber. And what's happening is it's heating near the bottom, and then as it gets hotter and hotter, it rises buoyantly to the top of the whole chamber, the boundary layer. And there, which we'll see hopefully soon, there it cools down and then actually comes back and in a form of a circulation, almost like a flow. Yeah, so you can see it here, where it goes all the way to the top of the boundary layer and then returns back down in this flow back to the surface. So if you've ever been to the desert, you might have experienced this as well, where there's no wind and then suddenly a gust of wind will hit you and then nothing. And then from the other side, another gust will hit you. And what's happening is it's buoyancy causing instability in the atmosphere, which again is important for Mars in particular, because water is lighter than CO2. And so you have these narrow buoyancy-driven updrafts that go all the way to the top of the boundary layer, which can be up to 11 kilometers on Mars, which then cool down and come back to the surface in these wide downdrafts. And they can cause shear at the surface. And you can feel them as these sort of random gusts that change their direction. And how high are they? They're as high as the boundary layer. What's the velocity scale? that depends on a bunch of things like the roughness, the height of the boundary layer, and buoyancy. But remember, we were talking about this famous paper by Ingersoll saying that ice could not melt. So we sort of analyzed the equation that he was using, and it turns out it comes from buoyancy over heated plate. So we'll quickly go through the terms. How much mass is being evaporated depends on the humidity, the viscosity, the density, and diffusion. And so it comes from an engineering-based formulation for heating a plate, essentially. So it only accounts for buoyancy. It does not account for the roughness or the height of the boundary layer, which, as we just saw, these large-scale gusts crucially depend on the height of the boundary layer and how rough the surface is. So we concluded that you cannot ignore the roughness or how high the boundary layer is. So this equation would work in a lab setting where everything is smooth, or on a small scale, but not on a planetary scale. So we wanted to see what effect would that have if you used it on a planet using the conditions Ingersoll assumed, which is the surface and the atmosphere at the same temperature, at the melting temperature of ice. There's sort of an extreme case, there's no water in the air at all, and there's also no wind. And so here's the atmospheric pressure. Mars is around 7 millibars on average, Earth is about 1,000. And this is the amount of energy you're losing when you sublimate turn from ice to gas. So about 800. And then some history. Ingersoll was a professor at Caltech. Byrne was Ingersoll's student, and Dundas was Byrne's student. And so they redid and revised his equation to come up with this line. And then we ran our model for a high roughness case where there's a lot of gustiness. And this is not a magic knob. It's something you can actually measure if you have wind speed measurements, and a low gusty and smooth sort of surface. So essentially there's this 2x, a factor of 2 variation that you can have. And why is this important? Because the amount of sunlight maximum on Mars is somewhere around here, if I remove this. And so this is what Ingersoll was saying, that if you're losing this much energy from evaporation alone, there's just not enough solar energy to heat up the ice to the melting point and then actually melt the ice. So if you're losing less energy, then there may actually be enough energy to melt the ice. So that's what we're trying to understand. And why there's a difference is, again, they're ignoring the roughness and these gusts of the surface. And here I showed this one simplified case. When we explored a bunch of cases, you can basically have errors of up to 450 watts per meter squared or 65. And all that depends on how rough the surface is, the wind speed, things like that. And what's next is putting these two pieces together into a new ice energy balance model for Earth and Mars. And so I had written a NASA Solar System Workings grant to put these factors into an existing snow thermal model called SnowTherm. And I'm working with Rachel Jordan, who actually made that model. And it's a snow thermal model for mass and energy balance. And it computes all kinds of things, the liquid flow and phase change and things like that. But it was for snow on Earth. And so we're expanding it to snow, firn, and glacier ice with and without impurities on Earth first, and then expand it to Mars. And here's sort of a example. So these are the measurements from Liston. So this is where the subsurface melting was happening in firn and glacier ice. And I realized it may be a little confusing. I just sort of added this recently. So I'll walk through it. So here's temperature on the x-axis, depth on the y. And the red points are measurements made in 1997 in January at 3 a.m. And so you can see it's melting below the surface and then getting colder in firn. And then also in glacier ice, it's melting below the surface, but deeper because the ice is more translucent as the grains get larger. And then the purple lines are listed in 99 model the temperatures from January 1st to January 20th, 1994. Because unfortunately, to drive the model, you need met data, meteorology data, like wind speed, things like that, which they did not measure at this place. So they had to use measurements from a different year from a nearby station. And that's the purple lines. and then we redid what they did in 99 with our model and got the black line. So uh, it's not the best comparison because there were no direct measurements of what is needed to run the models, but which is why we show 20 days of range. But anyway, that's kind of what we're working on right now. And okay, to summarize, small amounts of dust and larger grains can lead to 10 times more heating in dusty ice. Sunlight heats ice in the subsurface because it's translucent, but the heat gets trapped inside, like in a greenhouse, which can lead to stable liquid water being produced within the ice. And then accounting for roughness and the height of the boundary layer can lead to more or less cooling, up to like 450 watts per meter squared or 65 watts per meter squared. And yeah, that's it. And I'd be happy to take questions, and um, feel free to send abuse or comments to my email. And yeah, big thank you to Steve Warren, Phil Christensen, Gary Clow, and Rachel Jordan, and lots of friends and family. And yeah, I'll go back to my summary slide and be happy to take questions.
Okay, so does anyone have any questions? Could you indicate in the chat or type your question in the chat? Tyler Meng, do you want to unmute yourself? And
Yes. Hello. Can you hear me?
Yes.
Awesome. Thanks for the talk. That was really cool. Yeah, so I'm wondering about your energy balance model if for the subsurface melt, if you had to consider anything like the geothermal flux or like a depression of the melting point from the composition of the dust, like any salts or anything like that.
Yeah. For geothermal heat, um, right now, what we've been doing is it doesn't there generally the heat fluxes from deep inside are pretty small. So what we do instead is, and we're not measured at these particular places. So it is included, but what we do is to initialize the model, you'll set a grid up of ice or snow, whatever, that's 15 meters, let's say, thick, so thick that the annual cycle of temperature variation is sort of accounted for by being so thick. And in that case, then you impose a boundary condition at the bottom where there's no energy coming in from the bottom because it's accounted for in this. And then you run this model for every hour of the day for 1 year and then repeat that same calculation many times. And they call it like spinning up a model or for convergence. And so that's what we're doing for geothermal heating. And then for, yeah, in terms of the melting point depression, no. The amounts of dust are small, less than 1%. It could be that they, if you're talking about the Earth calculations, they did not measure or the amounts of dust if they were, I'm sure there was some sort of impurities, but it was not measured. And so, and for Mars, I don't know if there's an accurate constraint on the amount of salt inside dust on Mars, to my knowledge. And yeah, any sort of impurity will depress the melting point, but the concentration is important. And so I don't know if the concentration is large enough for the dust for, and if we even know if there's salts inside the dust in particular, or if they're just in the regolith. Maybe they probably are, but right now we're not accounting for salts at all. Yeah, because we think this ice formed from snow.
Thank you.
is there anyone else with a question? Andrew Bliss, do you want to unmute yourself?
Sure. So I just have like a fairly basic question. The percentages of dust that you're referring to, is that, you think about that kind of volumetrically or percentage of the surface that's covered? How do you think about that?
Yeah, sorry, I should have mentioned that it's by weight, by mass, in a mixture,
Okay, sure.
not in air. Yeah.
Anyone else with a question for Aditya?
Just as a comment, I really enjoyed the visuals and seeing the spectral breakdown of albedo and things like that. So that was good to see.
Yeah, thank you. Thank you.
Yes, it's actually fascinating how little how little sediment you need to make your ice look completely dirty.
Mhm.
That was a real surprise to me. Roger, do you want to unmute yourself?
Yeah, first of all, thanks very much. Absolutely fascinating talk. It's a bit of a tangential question, but conveniently, you've got the picture I was interested in on your slide 75 there. It's actually about those lozenge shape expansion and contraction kind of plates. I remember a sedimentology colleague raving about those in the fossil record, and somehow the name Gilgai has remained with me as to what they're called. But do the dimensions of them, the amount of gap between them, or anything, does that tell you anything usefully mechanical about the how the ice underneath is responding to temperature changes and so on?
Yeah, and I have not analyzed them myself, but there has been a lot of work analyzing, because even at the one place on Mars we've seen ice at the Phoenix landing site, they found the same, and where they dug up the ice and saw it in situ, there as well, they noticed there were lots of these polygons, and that people have analyzed the spacing and the things you mentioned and compared them with the Earth and even modeled how much ice there would be and how far deep it would be. And so there are papers by Mike Mellon as well as forgot the other person's name, but yes, people have analyzed them including at these gully areas.
Yeah, fascinating. Thanks. And if I can grab a moment for another slightly more focused question, your previous slide 74, you were showing us these really interesting models. That's the one. I'm a seismologist, and one of the things that's often interesting is some of the arrivals we see are very near offsets for seismic surveys on Fern, and they're rather anomalously high frequency and fast. And I'd be interested to extend models like that, where you've got a little bit of melting just below the surface, into the seismic properties, physical properties, and so on, and see whether or not there might actually be some evidence of that in any of our field data.
Yeah, that would be interesting.
Yeah.
I should mention though that the subsurface melting process is rare generally on Earth
Okay.
overall. And the reason for that is normally all kinds of ice on Earth are covered with snow, and snow is so, because of the scattering at the surface, it's so bright that barely any light goes into the ice or the snow. So in snow, there's very little energy, solar radiation going deep. And so as a result, you have less of this subsurface heating. You have to have more. And so at these places, it's very windy in Antarctica. And so it's rare that a lot of the snow or all the snow is actually being blown off, exposing the bare ice underneath. And even then, I think Liston wrote another paper examining the sensitivity to the environmental conditions. And if you had a little bit of cooling for air temperatures and more cloudy days, you would no longer have subsurface melting. So it's sort of on the edge of plausible or possible conditions. Yeah. Although on the other hand, it's getting warmer overall, so there may also be more subsurface melting, but you need to have no snow at the surface or bright surfaces.
Yeah, smashing. Thanks very much. Really good talk. Enjoyed it.
Yeah, thank you.
I think we're running out of questions there, so it just remains for me to say a huge thank you to Aditya Khuller for this really fascinating talk on Mars. I love ice on Mars. It's just so different from Earth, I think, and it's just really fascinating to see how everything works. Just to let everyone know about the next seminar, which is on the 12th of March. We have Livia Jacob talking on glacier mass balance into comparison, the Glamby exercise. So hope to see many of you there. But thank you very much indeed, Aditya. That was a really fascinating talk.
No, thank you for having me.
And of course, the talk will be on YouTube in a few days so that people will be able to see it there as well. So,
Okay, yeah, brilliant.
thank you very much indeed.
Yeah, thanks so much.